So let's look at some other important aspects for shaft design. So we'll be talking about the effect of residual stress and resonant frequency in this lecture. So residual stress, so the key here is that when you have stress concentrations that arise, when you apply some sort of tensile stress to the component, then it can result in a compressive residual stress due to the fact that basically it's going to want to yield and that based upon the original stress concentration that you kind of calculate, it's it's going to tell you that, all right, this is going to exceed the yield strength. So as a result, instead of getting the stress spiking past the yield strength, then we instead get kind of a blunting of that stress level to the level of the yield strength, and then a spread in the amount of space, the amount of material that gets yielded as a result. And then when you deload, you get a residual stress. And again, this is a phenomenon that we see in relatively ductile materials. If we're talking cast iron, not so much. So the result of this phenomenon is basically the fact that the stresses that we may have calculated some values here for the stresses that kind of go up higher than the yield strength. So in this particular for this particular example here, the yield strength of this material is 300. So when we calculate we have a calculated stress value that goes above that, what happens is instead, when it goes up and down and up and down and up and down, instead, it hits that maximum of 300, and then when it gets deloaded, keeps going up and down, but it shifts the mean. So the amplitude is the same. The amplitude is the same, but the mean stress has been shifted downwards as a result. So yeah, so basically, when we're looking at our Goodman graph, what happens is that we would kind of go ahead and do our calculation for the loading condition, kind of like as we increase our loading, we're in this case we're assuming that it's following some sort of load line. So kind of we're increasing both the amplitude and the mean kind of at the same rate. But as it gets loaded up, basically, when you get past the point where if you get past the point where you're operating on this SY curve, so on this SY line, then basically the actual stress state at the crack tip gets shifted because you get some sort of residual stress, and that residual stress is compressive, and the effect that it has is that it shifts the operating point to the left, because it's applying a negative residual stress, so basically any residual stress that's there is going to be affecting the mean. So if you have a compressive residual stress, then you're decreasing the mean stress, shifting to the left here. And so as a result, we end up getting, say, if we're at this point B here, instead of this being the actual operating point, instead it shifts over to the left here. So that would be the operating point for that particular for that particular condition, because of the residual stresses that occur. So then you could use that. You would use this operating point here to calculate your estimate for the life of the for the lifespan of that component, as opposed to this one. So, for example, here they plotted the different the different lines corresponding to different SNs for different lifespans. So for the original calculation for B, that's past, that's past the 10 to the 3 line here, which is, so based, if we didn't take the effect of the residual stress into account, we would assume that if it was loaded up to, it was this like 220, maybe 220 MPa tension for the mean, and 200 for the amplitude. If we didn't take that effect of the residual stress into account, we would assume that this thing would last less than 1,000 cycles. Whereas if we do take that into account, what it does is it shifts our operating point over to this B prime here, and you can see the B prime point is between the 10 to the 5 and the 10 to the 4 line, fairly close to the 10 to the 4 line. So based upon taking that residual stress into account, we can basically say that, all right, this thing's going to last at least 10 to the 4 cycles, so at least 10,000 cycles, as opposed to based upon this estimate here, where I'd probably say, it's a fair bit past the 10 to the 3 line, so I'd probably say, I expect that thing to last, what, 900, 800 cycles tops? Certainly not much. So yeah, that would be a fairly significant increase in our estimated lifespan for the component in question. So I'll do an example later on once I kind of start getting into the example videos. Well, we're going to talk about the critical speeds for shafts here. So I'm going to post in the comments a few links to other YouTube videos kind of demonstrating the phenomenon. And I'll give you guys a few seconds to kind of hit pause on this and then go watch those videos. So, welcome back. So as you saw there, the critical speed is, it is a speed at which we have a tendency to get excessive deflection of the shaft that is rotating. And one of the key aspects here is that being above the critical speed is not necessarily a problem, because it's basically kind of at a particular speed, you have a tendency for the for kind of the shape that the deflections in the beam takes to form to form like this. So it's kind of similar to what we saw with the buckling phenomenon last semester, where at a particular load you have a tendency for it to kind of you have a tendency for the kind of the shape of the column supporting the load to have excessive deflections. And basically it kind of happens at a it happens kind of based upon the tendency for the load to correspond to a particular kind of shape. So here for shafts rotating, you have a few shapes that can occur. And the one that happens kind of at the lowest speed is the one that is like this. We could also have, let's see here if I can do this properly. I also have something like this. So that'll happen above the first initial critical speed. So basically at twice the original critical speed. That's the kind of the waveform that we're going to be seeing in the deflection of the beams, which could also lead to excessively high deflections. So determining those is kind of, we can determine the critical speed kind of based upon what sort of force it takes to deflect a beam a certain amount. And then basically, as it's rotating around, if based upon the tendency based upon the fact that gravity acts downwards, if we are basically going to have it deflecting such that the mass, when it gets back around, is still kind of being still deflected outwards, then that'll cause us that'll cause it to that'll cause it to basically continue that deflections. So the critical the parameters that we're working with here, there's a few kind of configurations of the a few configurations that we can kind of use to estimate that. So the K value that we got here, the shaft spring rate, so that'll be pounds per inch or newtons per meter. And that's basically saying if we had the shaft just simply supported and we put a certain amount of weight, applied a certain force to the shaft in the middle, how much deflection would we get per how much deflection would we need to push down in order to get it to deflect a certain amount? So how many pounds would we need to push down on the center in order to get 1 inch deflection in the center? So if we're modeling this as a single mass, then basically we can calculate the critical speed the natural frequency of the shaft in radians per second here, just based upon that value there divided by the mass. And again, our units, the way our units cancel out there, so we got K over M, so newtons per meter. A newton is a kilogram meter per second squared. So if we got newtons per meter divided by the mass, so that'd be kilogram meter the units for the K is going to be kilograms per second squared, and then dividing it by the M cancels. Stop moving that around instead of letting me draw. Kilograms per second squared, dividing by the M again, gives you another kilogram on the bottom, cancels out. So this units here is going to be per second squared, and then square root of that. So we're in radians per second there. If we want to and then just converting that to the critical speed in terms of RPM is just a matter of taking that and multiplying it by 30 over pi. Another way we can go about doing that is just taking, if we know what the static deflection of the beam would be when a mass like that was applied in the middle, then we can take g divided by that static deflection and then take the square root. Now, if we have multiple masses, then things start getting a bit more complex. Now, what we need to do there is we need to basically calculate the deflection of each of the masses. So like for each mass, D1 would be the deflection of mass 1. This W1 term here would just be its weight. So it's mass times G. But the D1 would be the delta one there would be equal to the deflection of the deflection of this point on the shaft based upon the combination of the static weights of all of the other weights. So it's going to be basically, a function of the displacement caused by itself plus the displacement caused by the second weight plus the displacement caused by the third weight, so on and so forth. And then you need to do basically the same thing for each of those. D21 plus D22 plus, delta plus D delta 23, so on and so forth. So the calculations that you need to do for those static displacements scales up with the number of weights that you're having. So for each, it's the number of weights squared. So again, it gets fairly complex as you increase the number of weights. For the shaft mass only, this is the formula that we'd use, where the delta ST here, that would just be the amount that we would expect this shaft to be sagging just based upon its own weight. So the amount of deflection it's going to be displacing downwards if it was just sitting there still under a distributed load that was equal to the gravitational pull. And realistically, basically, this formula here is basically taking the multiple masses one and treating it as a whole bunch of, basically as an infinite series of tiny little slices of the shaft. So again, when we do get multiple masses, it gets complex real quick, which can be quite annoying. So what we often do is basically find a reasonable estimate based upon kind of combining the effects that the how to say this based upon kind of getting an estimate of what each individual mass on the shaft would have on the critical speed, and then kind of combining them. So we can get a good estimate of that by, say, finding the critical speed based upon the first mass, critical speed based upon the second mass, critical speed based upon the third mass, and so on and so forth. Add up the inverse of the squares of those two, and then that'll give you the inverse of the inverse of the squares of all of those masses, including the mass of the shaft. We still want to be including this one here, and then that'll give us the inverse of the square of the critical speed, or the first fundamental natural frequency. And that'll give you a reasonable estimate. So again, that's the first critical speed. And again, I would like to emphasize, as we saw, operating above the critical speed is not bad, as long as you want to stay a decent amount away from the critical speeds, and because the deflections become the deflections at the critical speed are a maximum, but close to the critical speed, you're still getting excessive deflections. So a typical guideline is that you usually want to be at least plus or minus 10% away from the critical speed of this shaft. And if you are accelerating fast, then you can get past the critical speed without it causing a problem. You just need to speed up quick enough. And then you're not going to you're basically not giving the system a chance for those resonant vibrations to grow out of control. And as long as you do that, you can speed past it and then operate at a steady state above the critical speed without too much of an issue. So if you end up getting a situation where you calculated your critical speed and you can't justify making the shaft a lot stiffer in order to avoid having a critical speed that is below your operating point, then what you're going to need to do is accelerate past it quickly enough, and make sure that you're far enough away from it. But yeah, that should do the trick.